When a speckle of starlight winks out behind the silvery threads of Saturn, astronomers hold their breath. We are witnessing a cosmic dance set in the stark black theater of space, where Saturn's elaborate rings pirouette across the universe. These celestial halos, made of millions of icy particles, revolve in a delicate balance, their beauty matched only by their scientific mystery. What tales do they tell of the solar system's infancy, and what can they teach us about the dynamic processes shaping our cosmic neighborhood? Saturn is the jewel in our solar system's crown, famously adorned with rings that have captivated skywatchers since Galileo first peered at them through his telescope in 1610. The rings we observe today are vast, stretching up to 282,000 kilometers in diameter. Yet they are remarkably thin, some parts no thicker than a multi-story building. Comprised predominantly of frozen water ice, with a smattering of rock and organic compounds, these glistening bands orbit Saturn at incredible speeds, their particles ranging from the size of micrometers to meters, each in its own swift icy race around the planet. Early spectroscopic studies revealed the icy nature of the rings, but it was the Voyager missions of the late 1970s and the Cassini probe, which orbited Saturn from 2004 to 2017, that provided unprecedented detail. These missions showed us the rings in their vibrant diversity, featuring dense main rings separated by gaps and ethereal fainter rings. The Encke gap and the wider Cassini division, clearings in the dense structure, tell stories of gravitational interactions and the complex orbital mechanics ruling this natural satellite system. Through telescopes and spacecraft, humans have glimpsed the results of countless collisions that occur as these particles cluster and break apart. This chaotic yet strangely ordered environment is an ideal natural laboratory for studying accretion processes, akin to those that may have formed the solar system itself. The genesis of Saturn's rings remains one of the great puzzles in planetary science. While the exact timeline and process are still debated, the prevailing theory suggests that the rings are relatively young, having formed just a few 100 million years ago. This contradicts earlier beliefs that the rings coalesced during the solar system's birth. The leading hypothesis involves a catastrophic event, such as the collision or tidal disruption of a comet, an icy moon, or a protoplanet drawn too close to Saturn by its immense gravitational pull. Investigations into the age and origin of the rings gained momentum with the findings from the Cassini mission. Measurements of dust pollution in the rings and their mass suggest they may have formed during the time dinosaurs roamed the Earth, capturing a snapshot of a dynamic period in solar system history. This notion is supported by the gravitational interactions between the rings and Saturn's numerous moons. These moons' gravitational tugs not only sculpt the rings but also help maintain their structure and propagate waves through them, akin to ripples in a cosmic pond. Further, the role of gravitational resonances in shaping the ring's structure is integral. Mimas, a moon of Saturn, interacts resonantly with the rings, maintaining the Cassini division, a large gap that serves as a testament to the subtle yet powerful forces at play. These resonances are not just curiosities. Understanding them provides deeper insights into similar processes that may operate in distant exoplanetary systems, offering clues about the formation of planets and their rings. In essence, Saturn's rings are not merely an astronomical curiosity, but a dynamic system that holds secrets to the processes that govern the formation and evolution of planetary bodies. Through the lenses of powerful space telescopes and the findings from interplanetary missions, we increasingly view these rings as a delicate cosmic clockwork, a masterfully orchestrated symphony of ice and gravity.